Everyone, we will continue our discussion about Algorand today. In the last class, we saw the code for sortation. So, sortation uses this VRF, verifiable random function, which takes a seed and the role. Of course, this will change a little bit as the different steps in Algorand proceeds. But essentially, this VRF spits out a hash, something which looks like a random number between 0 and 1, and a proof which somebody, let's say this user who has this particular secret key SK, he can prove to somebody that this hash actually belonged to him, which corresponded to this SK. Okay, so the proof is given by this pi. Okay. So suppose he runs this VRF and he gets hash and pi. Okay, so how does he know whether he belongs to a particular committee or not, right? And of course, as we go from one step to the other in Algorand, this seed can be changed appropriately, right? So those details we can look at later on, but let's say there is a particular committee we are interested in which has some particular seed. Okay, and different users who are part of Algorand are going to use this VRF to get their hash and pi values. Okay, so suppose a particular user has SK and PK, let's say public key and secret key, right? So he gets this pair, and he can use this to prove later on that that this hash is indeed corresponds to secret key. Okay, so we said that he runs a while loop like this, and what is this BKWP? So it's just the binomial. So W is the stake of this particular user. Capital W is the total stake in the network, let's say in the whole Algorand network, and tau is the size of the committee that you want, right? So BKW is KWP is just a binomial which looks like this. W choose K, P to the power of K, 1 minus P to the power of W minus K. Okay, so this is small w. So we use this particular while loop, and we said that initially J is set to 0. Okay, and this is the number of sub-users of a particular user who has this particular public key and secret key. Right? At the end of this particular loop, J should tell him how many sub-users he has in that committee. Right? So you want to allow a particular user to have more than one sub-user, because after all, if he has a lot of stake, the small w is quite high, then maybe he should have a chance of getting more than once into the committee. Okay? So why does this work out? I mean, it seems very weird. We have this binomial function and this summation and so on, right? I mean, and as long as this particular ratio is greater than this particular sum, then we keep incrementing the number of sub-users. So it seems very strange, but if we look at it closely, it becomes clear why they are doing this. Okay. So what do we really want? So let's say that we list out the total stake of the person, let's say in this fashion. This is, let's say, for each token that he owns, and we are only dealing with integer number of tokens. So this is 1, 2 and so on, and he has totally W tokens. Okay. Now I want to give him a number of sub-users in such a way that even if he splits this up into multiple keys, for example, right now he has W tokens corresponding to this public and secret key. But even if he splits this up, let's say, into 2 keys, so he gives, let's say, one set of tokens to one, let's say, PK1 and SK1, and another set to PK2, SK2, the chances, I mean, of his getting a certain number of sub-users should be the same. Okay, I don't want him to get any advantage either by splitting up these W tokens into multiple key pairs, or combining, let's say, tokens of multiple key pairs into one key pair. Okay, we don't want him to get a higher chance. Okay, so what do we really want? So we want tau, roughly tau sub-users to be there in a particular committee. Okay, so this committee size is given in number of sub-users, and the total number of tokens is in the entire network is capital W. Right, so it's roughly what we want to do is something like a coin flip, and for each token that a particular user has, we want to flip a coin, and with probability P, we want to choose a sub-user corresponding to that token. Okay, so we want to do this for all tokens for all users, but let's focus on this particular user. So you want to choose this with probability P. Similarly with probability P and so on. So suppose we flip a coin for each of these and we choose them with probability P. Okay. So roughly after we've gone through all tokens in the network, not just for this particular user, we will have roughly tau sub-users, right? Because we are selecting each of these tokens. We are just dividing the total stake in the network into tokens, and for each token we are choosing with probability P. Okay? So for this particular sub-user, we are going to do this for each of his W tokens, and maybe he gets 0 tokens, in which case he is not part of the committee, or he may get one selected, any one of these, and based on that, or he may get 2 or 3 and so on, right? And based on how many of these are selected, he will have that many sub-users in the committee, right? So essentially we want to flip a coin for each of these tokens, and we choose each token with probability P. That gives us the total number of sub-users. So how do we do this in an elegant fashion? I mean, you don't want him to generate a random variable as such, right? I mean, and anyway, it shouldn't be up to this particular sub-user to do it. I mean, there has to be a deterministic way to do this, essentially it should be some pseudo-random method, right, to choose all of these, and you want to do it efficiently. And effectively what sortation is doing is it's using this method. So you have a while loop, right, and at the end of it you get the answer. So how is this really doing what we want? Okay, so what we want is we want to flip a coin for each token. Okay. So suppose we were to flip coins and choose this, then what would we really get? So what is the probability that k of these are chosen? So probability that k tokens are chosen is given by binomial, right? We are choosing out of W, we are choosing K with probability P. Okay, so this is what I mean by K tokens chosen. I mean that number of sub-users of this user is K. Right, so this is really a random variable which has a distribution given by this, right? So it's a binomial distribution. You could end up choosing 0, 1, 2 and so on, right, for different values of K, and maybe you have even W users in the committee, right, but maybe with a small probability. Okay, so what I want is a binomial random variable which gives us the number of sub users. Okay, so what is this? How do I get such a binomial random variable, right? And what we have from this VRF is this hash. Right, so the VRF spits out this hash and pi, and that's pretty much deterministic. Given the seed and given the secret key, it spits this out, right? But effectively it acts as a uniform random variable, right? Assuming the seed is random enough, this hash is going to be something like a uniform random variable between 0 and 2 to the power of hash len minus 1. Okay, so this ratio is really a uniform random variable between 0 and 1. And what this entire process is doing, it's converting a uniform random variable into a random variable with this distribution. Okay, so it's a standard trick that you would use in any simulation. So the simulator might be able to give you a uniform random variable between 0 and 1, and you can convert that to any other distribution that you want. Okay, there's a standard trick to do that, and really this is what we are really implementing that trick with this while loop, even though it looks somewhat tricky. This trick to convert a uniform random variable to any random variable with a desirable distribution. Okay, so this is just as an aside. So given uniform random variable u, which is from a between uniformly distributed 0 and 1, and we want, let's say, random variable x with the cumulative distribution function, okay. So given this particular CDF, how do we generate random variable x, right? So you're given u, you want to convert it to x, which has this particular CDF. So what you do is the following: you plot fx x versus x. Okay, and let's say that it has some distribution like this, CDF. So the maximum value of the CDF is 1. Okay, so you don't have to, it doesn't have to have a 0 value here. I am just showing x as a positive random variable, but it could be negative too, like you could have a Gaussian distribution and so on. Okay. So what you do is, given u, so you generate a random variable u between 0 and 1 uniformly. I'm just saying that u is, let's say, a realization of random variable u. Okay, so it's like you want a random number between 0 1, and that gives you small z, small u. So you just mark the value of u over here. Okay, and you just find out what is the corresponding value of x over here. Okay. Say realization of x. Okay, so it's a easy enough thing to do. So it's really what you're doing is you're doing f inverse of u, and that gives x. Okay, so it might seem a little bit strange, but you can look this up in any textbook, or you can figure out yourself why it should work, right? So effectively, on the y-axis you're choosing a random number between 0 and 1. Okay, so that's what you're given, a uniform random variable, and you just find an appropriate value. You go to this, you find out which value of x is going to give you fx of x equal to this value of u. Okay, and that is going to give you this. So for example, suppose u was larger over here, right? You would get a higher value of x appropriately, right, corresponding to this, and so on. Okay, and you can do this for any distribution. Okay, fx, any particular distribution, any particular CDF, right? So now, of course, here I've shown you a continuous distribution, but you can have even a discrete distribution in which you would have steps over here, and in fact that's what we would have for a binomial distribution, because the value of k is only integers. It doesn't take continuous real numbers. K is equal to 0, 1 and so on, right? So you would see this particular cumulative distribution function would have a step-like function. Okay, and how do you find this particular value of x? So of course here we are looking for a k value. We are trying to, so in our case, of course, let's draw it a bit differently. So here we have x is really a binomial distribution, right? So you have 0, 1, 2 and so on all the way up to w, right? And you would have some function which looks like this, right? And okay, I think let's say that we have and all the way up to 1, right? So here right, so there's something in between over here. What we are trying to do is we are going to throw a uniform random variable between 0 and 1, and we are going to try to find out where it hits this particular cumulative distribution function. Okay, so let's say we have something like this. So I'm just this particular while function is just going to calculate the CDF. So essentially what we are doing here in this summation is we are trying to find the CDF of this binomial distribution, and we are going to find out at what point for what value of j does the CDF cross this particular uniform distribution, right? And that's what we are trying to do. Right, each of these is just equal to one of these jumps in this particular CDF, right? So this is this jump this is just B0 WP, this jump is just B1 WP, and so on, right? So we are just adding these up in the while loop, and this is let's say this is the uniform random variable. We're finding out at what value of j does this actually cross this, and that is the number of sub-users that a person has in the committee, right? So this is what really this sortation function is doing. Okay, so anytime you want to form a committee in Algorand, right, so this tau value is chosen, which tells you how many sub-users you want in a particular committee, and each user known only to him computes the VRF. Nobody else knows the hash value that comes out, so nobody can do a DOS attack on him because knowing that he's in the committee, because they really don't know that that person is in the committee. But the user himself can find out how many sub-users he has in the committee, right? And he finds using this particular method that we show, right? So a user can vote in a particular committee, and the weight that his vote has is equal to the number of sub-users that he has in the committee, right? So somebody can say, I have 2 users in the committee, and he can prove to them, right, by giving them the proof from which is the pi value from the VRF, and his vote will be counted by other users based on that. It will be given weight depending on the number of sub-users he has in the committee, right? But of course if he doesn't have any sub-users in the committee, then he shouldn't be voting at all, right? Because you don't want to flood the entire network with votes of people who are not in the committee. So what we're going to do in Algorand is that we're going to form many committees. We're going to try to mimic what we had in PBFT, okay, and we're going to try to use things like quorums, but it's not going to be as straightforward, because unlike in PBFT where you have an assigned leader and you have a well-known committee of a fixed number of members, here you don't have that. You don't know who the leader is, so there has to be some sort of leader election, and you have to do this every time because you don't want the leader to be amenable to a DOS attack, right? And also you don't want to have the same committee all the time, so the committee members are not going to face DOS attacks, right? They are not going to be open to DOS attack. So you want to keep changing committees, right, over time, which is what makes Algorand a little bit complicated, right? So that's what we will discuss next. Now let's go into the details of Algorand's consensus. So they give a name to the protocol. It's called BA star. Okay, sort of a BA comes from Byzantine agreement, right? And this has two parts. One is called reduction, and one is called binary BA star. So to get some intuition about what these do, let's start first with PBFT, a quick recap of PBFT. And we know that in PBFT you have n nodes, so n is fixed. And we begin with a known leader. And these things are going to change a little bit when we go to Algorand. Right? So here the n nodes are fixed, and I mean you can't sort of add nodes or have a little bit more and so on over time, right? So n is usually, let's say, in the range of few tens of nodes, and the leader is known, right? And once in a while what you can do is you can have a leader eviction, which we had called a view change. So what were the phases that we had there? So first we said we are ignoring the client, but let's say that you have the leader first sends out something called a pre-prepare. Okay. So the leader sends a message to the others, then the others gossip among themselves. So they say what they are prepared to accept. And normally this should be good enough, you would think, but each person doesn't really know what the others have heard, okay, from the others at this point in time, from the other nodes, right? So there are several of these nodes here, and there is one leader. So then we have the commit phase. Again, there is a gossip among all of them. Right, and then of course they reply to the client. Okay, so mainly there are these three phases where there is communication between the different consensus nodes, right? And quorums are used over here. So a quorum over here is greater than 2/3 of n. Who agree on something. Right, so this is how it worked, and it got a little bit tricky. We had different things that we had to put in here, a certain, not just the view number, but we also had to put numbers for a particular transactions or blocks position and so on, right? So now suppose we want to change this. So now in Algorand we want to move away from this, and we want it to be permissionless and purely proof of stake. But at the same time, we want to have some sort of committees to be used in order to do consensus. So here, how do you even have a leader? So we need to have some leader election. And we also want to have DOS resistance. So we will use different committees. Okay, so we'll do something like this. At least it will have a flavor of something that PBFT is doing. But before we even have something like a pre-prepare, we have to have a leader election. So for every block, every time a block has to be created, there will be some sort of a leadership selection process. After this, of course, the leader can send out his block. And of course, the leader can be malicious, right? He might do some mischief, send out multiple blocks and so on, just to confuse everybody else. Okay? And it might be possible that in the leader election process itself, maybe two different people think that they are leaders just because there were delays in messages and so on, or maybe two or even more, right? And so given all of this, we need to have consensus about what the block is going to be. Right? But we will have to have some notion of a quorum, right, so that people can sort of converge on something or the other, right? And we may have to have a little bit of gossip. So just because somebody sees a quorum, it doesn't mean that everybody else has seen the quorum, right? So they may have to keep gossiping for at least another round and so on. Okay. So let's at a high level talk about what exactly is done in Algorand. Okay. So we're going to use committees. And committee members essentially identify themselves using sortation. Right, so this is going to happen all the while in the background. So like we discussed earlier, sortation helps in users identifying themselves as belonging to a committee, and it also tells them how many sub-users they themselves have in a committee. And nobody can do a DOS attack on them directly because nobody else knows who's in the committee. Right? If at all you have to do a DOS, maybe you should DOS the entire network. Right, because you really don't know who are, let's say, the 20 or 30 members in the committee. Right? Okay, so first of all, let's say you have a leader election. Let's just call it committee 0. You have a leader election, and then what you're going to do is that so how do you find out who's the leader? Well, there is a sortation hash. So this is what comes out from, let's say, the sortation, and you can have a method for finding out who is the leader using this information. Okay, so each particular user has this hash and pipe which comes out from the VRF. Okay. And suppose this particular user has J sub-users. in this committee. Okay. So by the way, what is proposed in the paper is that tau for this particular committee, so this is the expected number of expected size of this committee, the tau of this particular committee is 26. Okay, so the reason you want to choose it as 26 is because your actual number is going to be a little bit less or a little bit more most of the time, but you at least want one person to be elected to the committee, right? So that you will at least have one proposer for a block, right? So this is good enough for that. And what we can do is somehow we have to choose one particular user as being the proposer. So let's say that we give them priorities. So there's a priority for this user, and of course we could come up with some other scheme, but this is what I've got in my notes. So let's say we take hash of this hash value and I, for I going from 1 to j, right? So every particular user will be able to get this particular priority, this particular number, right? And what they are going to do is they are going to broadcast this. So every user in the committee, that means for who j is greater and at least equal, greater than 0 at least. So every user in the committee broadcasts his priority. And let's say largest of these is supposed to be the leader. I'm sure we can have a different set of rules. You can maybe take a minimum and so on, right? And you just want one person to be elected as a leader. Okay. So initially this person doesn't know that he's the leader, right? What he does is that he just runs sortation, gets his priority and sends it off. And now the leader will learn who he is by looking at the priorities of other users in the committee. Okay. So the leader will then generate a block and send it out. Okay. And if everything goes off well, this should work out perfectly, that only a single leader is chosen and a single block has been broadcast by that particular leader. Okay. But what can go wrong is that there are timers used over here. So remember that there is a broadcast network. So suppose this is a network and you have different members of this network, of this particular committee. So there are many other users, but those who are not elected to the committee, they are going to remain silent. Only those chosen for a particular committee, let's say this one and so on, they are going to send out their priorities, right? So this is broadcast into the network. So each of them will learn some information, but they have local timers. So after a timer expires, each of these users will see, do I have the highest priority or not? If I have the highest priority, then I assume that I am the leader. Okay? But because of network delays and so on, it may happen that two different people think that they are leaders and they might send out blocks. So let's think about it. So suppose this person, I'm calling him L1, this particular user thinks that he's the leader, and so does L2. Okay, but maybe L1 indeed has a higher priority. Okay, so suppose L1 is malicious, he can send out many blocks right, and maybe L2 is honest but he's not the actual leader, so he sends one block link. So, okay. Now the question is how do we achieve consensus? Okay, and actually what's happening is these blocks are reaching different people at slightly different times, and this particular leader might might try to hide some information from some people and so on. Okay. So how to achieve consensus? Okay, and here it's become a little bit tricky, but this is something like the pre-prepare phase which we saw in PBFT. Okay. So ideally we would like to choose one of these blocks, right? And there should be consensus about which is going to be the next block. Okay. So what Algorand does is, first there is a filtering process. It's called phase 1, which is called reduction. So what we're going to do is that out of all these blocks sent out, there are only 2 choices after reduction. Okay, so one particular block generated, that is one choice. And the second choice is actually an empty block. Okay, and in the paper they refer to these from their hashes. So this is called the block hash. Whichever of these is chosen, and this they refer to by calling it empty hash. Okay, and now that we have just 2 choices out of these many choices, unless here we had 4, but potentially there could be more. Okay, so here there are just 2 choices, so it's a binary decision to make, and that's where we have phase 2. This is called binary BA star. So consensus is achieved on either of these. Okay, so let's talk a little bit about reduction. So reduction itself has 2 steps. Okay, so in step 1, okay, so there is a new committee here. So remember, in every step a new committee is chosen. Okay, so we want to avoid DOS attacks, so keep changing the committee, right? So what we're going to do is that everybody has heard these blocks, right? Potentially everybody might have heard them, but it could happen that before the timer expires, some people have heard only certain subsets of these blocks, right? So they are going to have a method to choose from these blocks. Okay. So in this new committee, each person is going to vote, right? So again, he's going to wait for some time and he's going to vote. So each member votes for who it thinks the leader is. Or maybe I should say not who the leader is, but votes for one block. Okay. So depending on who they think is the leader, so suppose for example, let's say that somebody has seen all 4 blocks. He's going to see that this is the leader and he's going to choose one of these blocks using some well-defined mechanism, right? But maybe it's possible that somebody has only heard L2's block before the timer, so he might vote for this, right? Okay. So each member votes for one block from among the blocks created by whom this member thinks is the leader. Okay, so for example, lowest hash among blocks of L1, for example, right? Okay, and okay, so this is all done before a timer expires, right? So each member waits for a timer to expire and then he sends out this particular vote. Okay. So let's say this is done when a timer expires. Okay, so there could be, let's say that there are several votes. Let's say we said B1, 1, B1, 2, B1, 3, B2, 1 and so on. So each of these gets certain number of votes. And how do we count the votes? Well, it really depends on how many sub-users somebody has, right? So suppose a particular user has 5 sub-users, then his vote counts as 5, right? So just let me write that down. Number of votes of a user is equal to number of sub-users that he has in the committee. Okay. Yeah, so there could be, let's say, 10 votes here and 2 votes here and 1 vote let's say, right? Something like this. Okay, so let's have a recap. So what we've done is that initially a leader was chosen, and the leader identified himself based on the priorities sent out by other members of that initial proposer committee. And the leaders could be mischievous and sent out multiple blocks. Now what we did is we started the reduction phase, where a new committee was formed in the first step. So whenever I say step, you can assume that a new committee is being formed. Okay. So what we are going to do here is that this new committee is going to say which of these blocks it's willing to vote for. Okay, and this is like something like a prepare phase. So they have told each other which particular block they are willing to accept, right? And now there's an issue. I mean, let's say that 4 different blocks got votes. So which of these are we going to choose? Okay. So at least these have been identified by different members of this committee, and this is in step 1 of reduction. Right. So remember, first we have proposer phase, which is like pre-prepare. And now we have reduction, which is something like a prepare phase of PBFT. Right? So we said at the end of reduction, we only want one of these to be chosen. Right? So one of these is an option, plus the other option we are going to allow is an empty block. Okay? So how are we going to do it? So we're going to have a second step within reduction. So this is step 2 of reduction. So now what we are going to do is this, again we have a new committee. Okay. And okay, so how do we decide a new committee? Well, remember that in VRF you had seed, and role. So the seed will change from one block to the next, but from one step to the other, the role will change. Right, so different random committees are being formed with expected size tau, and of course you can change tau also for different steps. Okay, so initially for proposer we said 26, and of course you can have a different tau for different steps, depending on how big the committee you want to be. So we elected a new committee here. Now we want to use something like a quorum, like we had in PBFT. So suppose tau is the expected size of the committee. Okay. And what we have is to define this quorum, we use some other parameter t, which is like a quorum fraction. So if tau multiplied by t committee members So remember, members refers to the sub-users. Right? So each sub-user is counted as one member. Okay, so if you add the total number of votes of all the people who have voted in a particular way, so if the sum of those votes is tau times t or greater, okay, then we consider this to be a quorum. And you can guess that t is typically greater than 2/3. Okay, but Algorand would typically set this to be much larger than 2/3. It could be much higher, maybe 80% or whatever, right? Okay, so what are we going to do here? So all of these different committee members in step 1 have voted for different blocks. And now in step 2, we want to choose only one of these at most, right? Or we could even have an empty choice, right? Depending on what happens. Okay. So what is each member going to do here? So each committee member is going to vote for a block which had a quorum in the previous step. I should say maybe step 1 of reduction. Right, so it's something like you had prepare and commit and so on, where they look for quorums and then they vote based on that. So each member here is going to see, was there something like a quorum, and of course I am using this term somewhat loosely, so the paper itself may not use it, but essentially if any particular block, let's say B11 had more than tau times t votes, then if somebody heard that many number of votes, then he can vote for that particular block here. Okay. So let's see, suppose let's say member A has seen quorum votes for B11, then he votes for B11 in this committee. Okay. Now these particular sizes of these quorums are chosen such that you can have at most one particular block which has a quorum in this step 2. The quorum size is such that only one block can have a quorum in step 2 of reduction. Okay, you have to keep in mind that some of these committee members could be malicious. So somebody here, for example, in step 2 might vote for a particular block even though he didn't get a quorum in the previous step, right? That's because the particular member is malicious. Okay, so but if you have a quorum in this particular step who says that they saw a quorum in the previous step, then that cannot sort of be broken. Okay, so we are just talking at a very intuitive level, and the proofs, of course, rigorous proofs are given in the paper. Okay? So what do we have here? So you may have, let's say that these are the committee members. Let's say A, B, C, D and so on. And let's, for the timing, assume that each of them just has one sub-user in the committee, right? So let's say all of these vote for B11, and let's say over here, let's say these say empty block. Maybe they didn't hear, maybe they are honest, but they just didn't hear all particular votes for B11 in the previous round. Okay, and let's say that this one is malicious, and let's say he said B12, right? And maybe this is big enough for a quorum, right? Okay, so what do we have here? So people in the next steps, in the next phase, which we are going to call binary BA star, they are going to look at this and they will see, okay, they will look at this round and they will see that, okay, only this one had quorum, okay, and some of them may not have seen all these votes, so they might say that the empty is my choice. So let's say that phase 0 is the proposer phase, phase 1 is reduction, phase 2 is binary BA star. Okay. So in step 1, let's say you have various committee members. So these are again chosen by sortation. So let's say you have A1, B1 and C1 and so on, right? So maybe this guy saw a quorum, but maybe this guy didn't see the quorum. Right, so each of them has a particular timer, right? So they'll self-select themselves for a committee, and then when the timer goes off, they make a decision and broadcast some information, right? So these guys broadcast their information. By the time A's timer expired, he saw all the quorum, or he saw all these votes, which let's say was enough to become a quorum. Okay. This guy, unfortunately, maybe some of the messages got delayed also, maybe some of these were malicious or whatever, right? And he did not see a quorum, right? And so on, right? So some of them may have seen a quorum and some of them may not have seen a quorum, right? So this leads to some complications. So we are not done with consensus up to this point. Okay, we still have to go through a few rounds in order to converge on either B11 or empty block. So block hash is a hash of B11, and empty hash of course is an empty block. Okay. So how are we going to achieve consensus now in binary BA star? Binary BA star work. Yeah, so we said that in the previous phase 1 reduction, there was a block hash chosen, B11. Some people, like for example A1, heard a quorum for B11, but let's say certain others like B1 didn't hear any quorum for B11 due to some reason. Maybe the adversary didn't send some votes to B1 and so on. Okay. So some of them have seen a potential block hash and some have not. Okay. So how does the whole network achieve consensus on one of these, either the block hash or the empty hash, right? So phase 2 itself has multiple steps, and in each step a new committee is chosen, right? So let's be clear that there are actually, in some sense, there are 3 phases. Phase 0 is where you select a leader who generates a block if he's honest, and if he's dishonest he might generate multiple blocks, right? Phase 1 you have reduction, which itself consists of 2 steps where we end up with 2 choices, a block hash or an empty hash. And phase 2 again we have several steps. Phase 2 is the most complicated, okay? And so we have multiple steps in order to reach consensus. So what should we do to reach consensus? So A1 has heard a quorum over here, but he doesn't know that other people have heard a quorum. So he can't just sign off and say that I am going to decide on B11, right? There has to be some gossip among the different users, and we're going to let only the selected committee members broadcast some information, not everybody, right? So they're going to use sortation to decide if they are in a particular committee, and they will send out some information. So what should A1 do? Let's think about it. So A1 has heard block hash. So what is he going to do? He's going to vote for the block hash. Okay, and he hears some information. So should he, what should he do? Suppose he hears a quorum for block hash, what should he do? So what we want to do is, if A1 gets quorum for block hash, in step 1, then A1 has achieved consensus on block hash. Right? So this is quite ambitious claim. So A1 has voted for block hash, and he saw quorum for block hash in this particular step, and we can say that he has achieved consensus on block hash. But the question is that true? I mean, what about other people? Maybe what if they didn't hear a quorum for block hash? So how can we make such a claim that A1 has consensus over here, right? So this is a little bit tricky, and how do we enforce it? So one way we are going to enforce it is that since A1 has achieved a quorum here, we know that other people have not achieved a quorum on empty block. others have not in this round, in this step. So I shouldn't use the term round, because in the paper, round is really it refers to the block depth in the blockchain, right? So we shouldn't get confused about that, right? So let's not use the term round, let's just talk about steps. So we know that others have not in this step. So I mean, people are unlike A1. So people who have achieved, if A1 or in fact any other user has heard a quorum for block hash, then the A1 or that other user who has heard this has achieved consensus. Okay, so others have not in this step got a quorum for anything else. And of course there are only two options here. I mean, you can only have block hash or you can have empty hash. Okay. So what happens to these? So these have a timeout. So there is some timer and you count votes up till that timer. Okay, so we said A1 has heard a quorum by the time the timer expired. But others time out with no quorum. Okay. So what do we do now? So we said that these guys have achieved consensus, and essentially everybody better reach consensus on the same thing, otherwise we are in trouble. But these people didn't hear this quorum. So what is going to happen? So we've left, we are considering this particular case. So now what we are going to do is we are going to try to reinforce this quorum in the next vote. So specifically for this particular occurrence, and of course you'd have to look at other cases, right? So if this particular if this happens in step 2, what should we do? So all people in this set, let's call them this set, let's call them, let's say some let's call them set Y, right? All of them have got consensus on block hash in step 1. Step 1 of phase 2. Okay. So what are these people going to do? We are going to force them that if they are selected in a committee in the next step, they will vote for the block hash. Okay, and what about these folks? These also, we force them to do the same. Okay, so we're sort of pushing things towards block hash, right? So of course we are assuming that let's say these particular nodes know the value of block hash, right? So they could, let's say C1 knows block hash, but it didn't have a quorum here, then C1 would actually vote for the block hash. right? Okay, so for explanation, I'm going to assume that all nodes know block hash. Okay, so let's say that there were lots of people. Okay, so this guy, let's say that many of them voted for block hash, but some of them heard a quorum and some of them didn't. Right? So these of course have heard a quorum for block hash, they vote for block hash if selected in the committee, and in fact they do it for multiple steps. And step 3 and 4 also. Okay, so for 3 different steps, all these people are going to keep shouting block hash whenever, if at all they are selected, right? If this thing happens. So if you have not achieved a quorum in step 1 for block hash, right? Then what you're going to do is, you know what block hash is, you would still vote for block hash in the next round. Okay, and these two will hopefully get you past the post. Okay, and so hopefully ensures all here quorum for block hash. Okay, so suppose it happens, so these set of people heard a quorum, some didn't, but we are assuming they knew the block hash value, but they timed out, so by default they are sort of going to vote for block hash, and these people have already achieved consensus, so they are anyway going to keep voting for 3 steps for that. So hopefully this is going to ensure that more and more people are going to hear consensus for, are going to hear quorum for block hash. Okay. So what we want to do is that if anyone hears a quorum for either block hash or empty hash, then reproduce that vote in the next round, or reproduce that as its vote if in the committee, right, if selected in next step. Okay, and we've looked at one particular case, right? There are many different cases, which is why the pseudocode even of binary BA star looks very tricky. So we are saying that, let's say in the first step, some nodes saw quorum for block hash, and then they achieved consensus on it, right? So others of course didn't know about this, but they got a timeout, we know that, and by default they say that, in step 1 I got a timeout, so I'm going to vote for block hash in the next round, right, in the next step. And in that particular, at least for this particular case, we saw that we are pushing people so that everybody is going to hear quorum for block hash, and then they are going to vote. Let's suppose this ensures that most people have heard quorum for block hash. Again, they would keep voting, like these folks and even other people who hear a quorum for block hash would keep voting for block hash in subsequent steps. Right? So hopefully I have given you some intuition about why we would everybody would converge and they would see quorum repeatedly for block hash, right? Now but of course we talked only about a special case in step 1, that certain set of nodes got consensus for block hash, right? What if there was no consensus, let's say, on block hash, nobody achieved consensus for block hash in the first step? Then what should we do? Right? So suppose there was let's say there was a consensus on empty hash. Then what do we do? Right? So let's look at another case. Suppose some set maybe I use the wrong term, consensus. Suppose a set y got quorum for empty hash, and y bar, the other set of nodes, got no quorum, just the way the quorums are set up. Okay. So we said that these people, so they time out. Okay, with no quorum. Okay. Maybe they heard a few votes for block hash, but they didn't get enough to achieve a quorum, right? And they didn't hear enough empty hashes too. So what would happen here? Now these people are going to vote for block hash. Okay. Okay, so we don't say that these particular nodes have achieved consensus on empty hash, right? And but let's see why. We'll go ahead. Let's say that we see about what happens in step 2. So we said since these nodes have got a quorum for empty hash, in step 2 they should vote for empty hash. Okay. But the thing is, we said by default, if in the first step y bar did not get any quorum, then they would vote for block hash, right? So you see that there is an imbalance, though these people are fairly sure because they got a quorum for empty hash. It's not getting reinforced by these other votes. Okay, and so whenever I say vote, I mean if they are selected. So keep that in mind. So if selected in the next committee, and here too, if anybody in y bar is selected. Okay, so there's a mismatch over here. Ideally, we want to reinforce the votes of both of these parties so that they ensure that everybody gets to hear, more and more people get to hear the same vote, and we achieve consensus, right? Everybody gets to hear a quorum, right? So it's possible that at this particular step 2, not everybody has heard a quorum for empty hash, right? Whereas in the previous case, we saw that these people were voting for block hash as well as these. So it's very likely that everybody is going to hear block hash. So here again, these people vote for empty hash using the rule that we said. If anyone has heard a quorum for either of these, then reproduce that as its vote in the next step. Right? Now, what happens now? So suppose somebody does not hear a quorum in step 2. Suppose he times out without a quorum. Then what should he do? Okay, so let's just call it so let's say that set Z, here's quorum for, let's say, empty hash in step 2. And Z bar by the timeout here's no quorum. Okay. So what are we going to do over here? So in this particular case, we want to give the sort of push everybody towards accepting empty hash, right? So what we are going to do is we are going to do the reverse of what we did earlier. So these people by default vote if selected for empty hash in step 3, right? And these, of course, by they are going to vote for empty hash, and again if selected in step 3. Okay, so first we are saying if somebody gets quorum for block hash in step 1, we are going to push everybody. Then pretty much by step 2 we are done. Everybody is going to hear, because even those who didn't hear a quorum are going to default towards block hash, and by step 2 we are done. We have achieved consensus for block hash. In this case, let's say we are saying that some people got a quorum for empty hash in step 2, others didn't get a quorum, and then we are going to try to push towards empty hash. Okay, and we are going to do that by everybody defaulting, okay, to everybody who doesn't get a quorum is going to default towards empty hash in step 3. Okay, so here is the idea, and I'm sure we can look at other cases too. We've looked at 2 particular cases and we've seen how we are converging. So one case we said that somebody in step 1 gets a quorum for block hash, and then we showed how things will get pushed towards block hash. Here we are saying we have a set which got empty hash, quorum for empty hash in the first step. Okay, and we are saying how we are converging towards empty hash. So by step 3, hopefully we are done. Right, so what we are going to do over here in this particular case, okay, so in step 2 they got these people got quorum for empty hash, so we say they have got consensus on empty hash. Okay, and to ensure that in fact everybody gets consensus on empty hash, we force people who didn't hear any quorum to vote for empty hash in the next round. Okay. So this is at a high level what binary BA star is doing. It's sort of in the first step it prefers block hash. If there's a quorum over there, they want to push everything, push the consensus to block hash. But in step 2, if there is a quorum for empty hash, then you want everybody to say that empty hash is the consensus choice. Okay. Now what the authors of the paper show is that an adversary can even mess up this. I mean, it's possible that you don't finally achieve consensus, that maybe you don't have a quorum for empty hash over here. So maybe you have a quorum for empty hash in step 1, but there is no consensus here. Okay, we are still preferring block hash in step 1, okay, because by default these guys are going to vote for block hash next. Okay. So maybe what the attacker will do is he will ensure that there is let's say that you never converge anywhere, that I mean you don't have quorum for block hash in step 1, and you don't have a quorum for empty hash in the second step. So let me write that down. So the paper shows attacker may succeed in ensuring no quorum for block hash in step 1 and no quorum for empty hash in step 2. Okay, so nobody terminates, nobody says that I have got consensus, right? So what should we do? So they have yet another trick, right? So the thing is, the reason this attack is able to succeed is that the attacker knows what we are trying to converge on in step 1 and 2. He knows that in step 1 we are trying to converge to block hash, so he ensures that there is no quorum there, right? And in step 2 he knows that we are trying to get quorum for empty hash, right? And if there is a quorum for empty hash, then we will, the rules will ensure that everybody gets that quorum subsequently. Okay? So what they do is they make it difficult. So they, in step 3, okay, so what they are going to do is that if somebody times out, with no quorum being heard, okay, then but what we are going to try to do is we are going to make it pseudo random. In the next step. Okay, so let's actually look at the code to understand this. So this is binary BA star from the paper. Okay, and some of the things we've already discussed. For example, This is the triple vote in subsequent steps for those achieving consensus. Okay, so similarly for here, so this is, we have this while loop which can go on up to maximum number of steps. Okay, so this would normally be step 1, okay, and this would be step 2 in the first iteration. First iteration of the while loop. Okay, so we've talked about this, and this is if I didn't get a quorum. Okay, then by default I'm going to vote for block hash the next time. Okay, so this value of R is set to block hash, and I'm going to vote for it over here in the next step. And similarly here, if I didn't get any particular quorum, so let's just say this no quorum, then I'm going to default to vote for empty hash in the next round, and I'm going to make that work out. Right? Okay, but there is still an attack possible, like we just discussed. So what they do over here is, so of course here the committee, this is just a vote. I'm going to vote R in the next step, right? So round refers to the block depth, so we'll just ignore it for the time being, right? Right, this context refers to the entire blockchain till now. Okay, so let's ignore that, those are not so important right now. So you cast your vote and you count, okay? So by the way, committee vote is going to also decide whether you are selected or not, right? So everybody is going to run this, and I'm going to vote, but it's assuming that I'm voting only provided I'm selected in the committee, right? If I am not selected, then I would just not send out anything in the committee vote, but I would still count votes. So everybody is counting votes even if they are not in the committee and so on, right? So in step 3, I'm going to count the number of votes, and if there is no quorum again, then what do? I don't want to let the attacker to keep ensuring that there is no consensus, right? So what I do is that this common coin, which is generates a pseudo random number. Okay. Yep. So it cannot be predicted by the attacker, right? So the attacker knows in step 1 by default these people are going to vote for block hash, right? And he knows that in step 2 they are going to vote for empty hash. Here he doesn't know that, which makes his attack quite difficult. I mean, it depends on what this spits out. If it is 0, then by default they vote for block hash. If it is 1, they would vote for empty hash in the next round. Okay, and that sort of kills that special attack that the attacker might be able to do. Okay, so this is sort of at a high level what is happening over here, and the authors prove that with very high probability we are going to achieve consensus. All honest users will achieve consensus using this particular binary BA star. Okay, so Algorand is quite a tricky protocol. I mean, it's very, very tricky. They're trying to do something like PBFT, but with different committees. Okay, they want to prevent a denial of service attack, so they're coming up with different committees. And also they have to deal with the fact that the leader has to be elected every time, in every round when a new block has to be generated. Okay. So Algorand, of course, is quite a famous protocol, especially because of Silvio Micali, and there is even Shafi Goldwasser, for example, who's also a Turing Award winner like Silvio Micali, and they are all involved in the Algorand team, right? And the good things, what are the good things about Algorand? It's pure proof of stake, and another thing is that there is no deposit. So it's pure proof of stake. There is no proof of work at all. There is no deposits which can be confiscated. So this is unlike Slasher. Okay, and other proof of stake protocols too, they say that if somebody misbehaves, we are going to steal his, we're going to confiscate his deposit. Here there are no deposits at all. Okay. Here pretty much there are no forks, so you achieve consensus in a particular round. So with the synchronous networks, there is no forking, so it's almost like PBFT. Okay, so it's quite remarkable. Of course, if you don't have a synchronous network and many people don't hear a lot of votes and so on, then there could be a period where there could be some forks. Okay, and so what they say is, suppose there is a fork, so suppose you have synchronous time period, then blocks keep getting added one after the other, but then you have weak synchrony, or right, so let's say you don't know what the upper bound is and so on, so you can't set your timers and timeouts appropriately. You may have a fork. Something like this happens in the network. Okay. So then what do you try to do? Okay, so suppose this might happen. Okay. And what you could do is you could reuse this binary BA star to decide on one of these. So if a fork occurs like this, right, you can reuse the protocol. Okay, so I was looking at Micali's talk. So you can use consensus for many things. You can use the Algorand consensus protocol for many things. So it's not just to decide what is the next block. You could use it maybe to resolve the forks. Okay, so suppose you have a synchronous period. Okay, so you can choose between one of these, okay, to resolve the fork, right? Or what he says is that you can even decide to change some rules in the protocol. Okay, so instead of saying that everything is cast in stone like in Bitcoin, and then people have a fight, and then they decide to have a hard fork and so on. So here what you can do is you can change rules, okay, based using, let's say, the same consensus protocol, right? So, and of course he doesn't elaborate too much what sort of rules would you want to change. Maybe certain, you want to add a new programming language, let's say, right, to the blockchain. You might want to use some consensus. So somebody could propose a change, and you can decide by consensus whether we are going to go for it or not, right? So anyway, this is Algorand, which is quite a well-known protocol. It's one of the more well-known pure proof of stake protocols, right? So whether it's going to become big or not, we'll find out. Only time can tell.